So I thought I'd do a little bit of a review of the linearization stuff, since hopefully that was your topic for today. And then I'm going to do a related rates problem that looks similar to one of your homework questions. And then I'm going to do a differential question. So kind of a mixture of the last two lectures. When you're doing a linearization, you want to choose a number that's close to the number that they're giving you. It can't be too far off or your approximation will be bad. So it has to be pretty close. So when it says use a linearization at an appropriate center, that's the A value up in our formula. The A that you want to pick needs to be something that is like easy for you to do the calculation at. So for us, for number one, I would want to choose A is equal to 81 because I actually know how to take the fourth root of 81. I don't know how to take the fourth root of 83 or 84 or 85, but I need something close. I can't go too far off. Other things that you need, in order to use this formula, we're going to have to find the derivative of our function. So I need to know what my function is. So
Fourth root of x.
Yeah, that would be a fourth root of x. Or another way to write that would be x to the 1/4 power, which might be helpful when you do the derivative part. And if you have 1/4 and you have to subtract 4/4 from it, you'll have -3/4.
So that would be something cubed.
So we could write that as 1/4 times the denominator is the root. So this is still a fourth root of x cubed. Is a way you could write that to do your calculations.
Which would be 83 cubed.
So
using A equals 81.
yeah, when we do our linearization, I'm plugging in 83 for the x, and I'm going to do f of 81 plus f prime of 81 times x, which is 83, minus a, which is 81. So f of 81, that's us taking the fourth root of 81, which should just be 3. We did that on purpose because that was the one that we could calculate nicely. To do f prime of 81, I need to come over here to my simplified version of the derivative. And if I plug in my 81 down here, 81, I probably don't want to have to cube that first. So instead, I'll do this calculation 1/4 times the fourth root of 81 and then raise that number to the third power. That's also legal.
3 to the third.
There you go. So 3 to the third would be 27, and 27 times 4 is going to give you 108. So this is going to be 1/108. And then we're multiplying that times 2, because 83 minus 81 is just 2. So this comes out to be 3 plus 2/108 is the same thing as 1/54. So 3 and 1/54. Which, if I did 1/54 in my calculator, that's gonna be 3.0185 if I round it. So this is my approximation. I got approximately that. how good is that actual value? Let's take the fourth root of 83. So 83 to the 1/4 power. My calculator says 3.0183, 3.0185. Pretty darn close to the correct answer. So it's a very good approximation.
I made a mistake.
Did you catch where it is?
Yeah, after seeing that.
Okay. So knowing that I want to choose my A in a way that's going to make me answering this part not hard. I don't want e to the 0.3 power. I don't know how to do that in my head, but 0.3 is really close to 0. So A equals 0 is a very good choice on this one. F of x is just e to the power of x. And you need the derivative of that,
Which is e of x.
which is also e to the power of x. So these ones are not too terrible. So for our linearization, we have L of 0.3 is equal to F evaluated at 0 plus F prime evaluated at 0 times our X, which is 0.3, minus our A, which is 0.
One plus one, 0.3.
So yeah, so e to the 0th power is just 1. That's also e to the 0th power, so that's also 1.
Times 0.3.
0.3. So this is going to come out to be just 1.3. It's an approximation, so I should put the little squiggly equal sign. Equals approximately. But what is actually e to the 0.3? E. If I can find the button on my calculator. There we go. E to the 0.3. My calculator says 1.349. 1.3. Pretty good approximation. Tan inverse of 0.98. Oh, sorry.
Whenever we do these, do we always have to write the squiggly in there?
I'm putting the squiggly in there to remind you that it's not the real number. It's us approximating it. So it's not that that would be a required thing. It's just in there as kind of to remind you it's not, that's not actually equal. That's us doing an approximation. Yeah. Tan inverse of 0.98. Bleh. But tan inverse of 1. Tangent is sine over the cosine. And so what is the one angle that is exactly the same for both? Pi over
2.
No. 4. Pi over 4. If you take the cosine of pi over 4, you get root 2 over 2. And if you take the sine of pi over 4, you also get root 2 over 2. So the tangent would be 1 because you take the sine divided by the cosine. And if they're exactly the same, then that would give us 1. So we want our A to be 1 for this one because 0.98 is pretty close to that. Okay.
Yeah. Sorry, I got confused with 10.
That's okay. So my function is the tangent inverse of x. So derivative of tangent inverse was this week. Do you remember what the derivative of the inverse tangent is? It's 1 over 1 plus x squared. Nicely done. Yep. Or x squared plus 1. Either direction is cool. That's our derivative. So we are doing L of 0.98 is equal to F evaluated at 1 plus F prime evaluated at 1 times 0.98 minus our 1. And so if we plug in 1, tan inverse of 1, we already said that one's pi over 4. That's the one angle where both the sine and the cosine give us exactly the same thing. And then when we plug 1 in over here, 1 squared is just 1 plus another 1. So this would be 1/2 over on this side. Is that okay? And then 0.98 minus 1 is 0.02, and it's negative because 0.98 is smaller. You don't need a calculator, I promise. What's half of 0.02? 0.01. Yeah, so it's negative 0.01. So we would say that this is pi over 4 minus 0.01. And that's fine to leave it that way. But if you were wondering what that is approximately equal to, we can figure that out. Pi over 4 minus 0.01 is approximately 0.775. And so how good of an approximation is that? Tan inverse of 0.98. My calculator says is 0.7753. It's a very good approximation. Very close.
3 digits, you got it.
Yeah, it was perfect. Okay. So the linearization problems, the hardest part of the linearization problems are figuring out the A that you should use. And it always needs to be a number close to whatever the number is that makes your calculation nice. So 83, I don't know the 4 through to 83, but I do know the 4 through to 81. So that's why we're picking that one. I don't know e to the 0.3 power, but e to the 0th power is easy. So we'll use 0 for the A. And tan inverse, there are not very many tan inverses I know, so I'm glad that's pretty close to 1. And 1, if it were like 1/2, that would still be a problem because when you're doing tangent, we have to have the sine divided by the cosine. So that's going to be like a √3 or a √3 over 3. Those are usually the ones that would pop out, but the 1 is the nicest of all of them. Questions on the linearizations? You got a few homework problems with those.
Okay.
Homework problems. One of them includes a coffee draining into a pot. And it says that the coffee is draining from a conical filter. So it's cone shaped. So there's coffee in here and it's pouring into our coffee pot, which is a cylinder. And they're telling us that both the cone and the cylinder have a radius of 4 inches and a height of 8 inches. So same dimensions. The coffee's draining from the cone into the pot at a rate of 10 inches cubed per minute. In the instant when the coffee in the cone is 2 inches deep, they're asking us 2 questions. How fast is the coffee level in the cone decreasing? So there's coffee in the cone and it's getting lower. And as that's getting lower, it's pouring into the pot. And so the pot's getting higher. So they're asking, how fast is the coffee level in the cone decreasing? And then how fast is the coffee level in the pot increasing?
Sorry, I'm getting it.
I just was setting up the problem. I went ahead and put the formulas on there for the shapes.
Oh, do we take the derivative of B? Okay.
So one of the things we want to consider is they did give us a rate in the problem. They said coffee is draining from that cone at a rate of 10 inches cubed per minute. So what they gave us is the dV dt is negative 10.
-10 in.
But they're asking us how fast is the coffee level decreasing? That's a change in height. So they want us to find dH dt, specifically when h is equal to 2 inches. Now, when I'm looking at this formula up here, I have h's in there, so I know I can get a dH dt, but I'm also going to end up with a dr dt if I leave that r in there, and they didn't give us anything to get rid of that with, so I want to get rid of that r before we go do the derivative part. So we need to use the information we have geometrically with this cone to replace the r with an h. So here's what they told us. The height of the whole cone is 8 inches, and the radius of the whole cone, like if right at the top, is 4 inches. But as we go down, the radius gets smaller and the height also gets smaller. So I want to make proportion. And so if I set up a proportion, I can say the radius is 4 over r if I want. So big radius versus small radius. And then for the heights, I can do big height over small height. And I want to replace my r with h's, so I need to solve for r. So if I want to solve for r, I'm cross multiplying. This is going to give me 8r equals 4h. And then if you divide both sides by 8.
So r equals 1/2 h.
Perfect. R is equal to 1/2 h. And so into our volume formula up here, I'm going to go ahead and replace the R with 1/2 h. So that's going to change this into, let's see, that'll be 1/3 pi times 1/4 h squared times another h would be h cubed. So my new volume, if I put it all together, I have 1/12 pi h cubed. And now we're ready to go ahead and do our derivative, because when I go take my derivative, I'm going to have a dV dt and a dH dt, and I won't have any other variables in there. So dV dt is equal to, we're going to bring that 3 down. 3/12 is 1/4 pi h, and then we're subtracting 1 from that 3, so it becomes just an h squared. But then I need a dH dt.
-10 divided by 1/4 pi h squared equals dH dt.
So dV dt, they told us was -10. And that equals 1/4 times pi times, they told us to plug in 2 for the height, squared, and then that's times dH dt. And we're supposed to go solve for dH dt now. So 2 squared is 4 divided by 4, so these are actually going to cancel, and we just have pi there. So if I divide both sides by pi, -10 over pi is my dH dt. Negative 10 over pi, in this case, my units would be inches per minute. So dHdt is negative 10 over pi inches per minute. So coffee's draining out of the cone. So the height is decreasing. So I'm not scared that we just got a negative number. The height should be getting smaller. That makes sense. So when we go to do this next part, it wants to know how fast is the coffee level in the pot increasing this time. If we've got coffee draining out of this pot at, we said we were using negative 10 inches per minute, how fast is it draining into this pot? Positive 10. So if it's draining out at negative 10 from the top one, it's pouring into the bottom one at positive 10 because we need this thing to be increasing now. So we're going to use positive 10 for dV dt for this problem because it's going into the pot. And you're again finding dH dt. Specifically when h is equal to 2. But we're using a different equation this time because the shape of the thing we're pouring into has this volume, pi r squared h. Now, in terms of the R scenario in this problem, we still have a problem in that I have too many variables. When I go to take the derivative of this, I'll have a dr dt and a dH dt, and I don't want the dr dt. But I don't actually have to go do a crazy math problem to figure out how to get rid of the R in this one, because let's look at this picture. The radius up here is 4. When we were doing it with the cone, the radius up at the top was 4, but as we went down, the radius got smaller, right? So we had to come up with a relationship for that. But as I go down on here, you see how the radius doesn't change on a cylinder? Even when I'm down here at this level, my radius is still 4. So I don't have to do a calculation. I just need to replace it with 4. So I'm going to replace my radius up here
4 squared.
with 4. So this is going to become 16 pi h is my volume formula. And now I can do my dV dt. When you take the derivative of 16 pi h, this is a constant, so it's just 16 pi, but then I need a dH dt. So my dV dt, we're going to use positive 10 this time, is equal to 16 pi dH dt. And so to solve for dH dt, I just need to divide both sides by 16 pi. Which we could make 5 over 8 pi if we simplify it. And that's going to be inches per minute. And since this is supposed to be a positive rate, I'm happy that this one doesn't have a negative number on it. That's good news. So the top one is supposed to be negative because the height is getting lower. This one, the height is getting higher. So you've got a homework problem that has this type of scenario happening. I don't know if it's coffee, but it definitely is. Liquid is pouring through a cone into a cylinder. Same setup. Any part of this you want to have me repeat how I did it or why I did it? Feel okay?
I think I'm good.
I'm going to do a differentials problem. So that should have probably been a topic you did today, I assume, before the linearization, maybe kind of, sort of. They don't spend a lot of time on the differentials usually, but there's a lot of words, but not really a lot to do. A coat of paint of thickness 0.1 inches is applied evenly to the faces of a cube. So think of a Rubik's Cube or a big dice. Sides are 10 inches on each of those faces of the cube. Use differentials to approximate the volume of paint used. So we put the paint on each of the sides and it's 0.1 inches thick, but I've got sides on a cube, top and bottom, or side to side, each direction, right? So we're saying that the paint thickness is 0.1 inches thick. And then this usually, like this note that I have in there, this would be a thing you're supposed to figure out in a problem, which it'll be the annoying thing where you go look at the answer and you go, why is the answer twice what I think it should be? And the reason for this one is that when we're trying to increase the length, so we're going to be talking about increasing, when you go to take your derivative here, you're going to have dV dt, that's going to be the volume of the paint, but the dx dt is going to be the increase in the side lengths. And when we're talking about the increase in the side lengths on this cube, if you start with a cube, I'm trying to think of a good way to think about this. Let's pretend like this is like one of the faces on the cube. Pretend it's square, not a rectangle. But if I put paint on this thing and it gets 0.1 thicker, then the opposite side, that's the back of it, is also 0.1 thicker. And so the whole length that direction is actually going to increase by 0.2 instead of 0.1, because you have to think about it made it longer in both directions. So we have to add them together. This is like me staring at problems and then going, why is the answer 2 times what I got? It's like, oh, because they have to double the side length. Okay. So the dx I'm going to be using is 0.2 instead of 0.1. And then in terms of what my calculation is going to look like, I'm not doing exactly the same thing when we're doing our related rates problems. When we're doing differential problems, I'm going to go ahead and find my dV, but it's not dV dt, it's dV dx. So I'm changing the volume in relation to the changing of the side length. There's no time that's happening here. So it didn't say anything about an amount of time. So we're not doing a rate. Okay. dV dx means that I'm going to put 3x squared and I'm not going to put anything after it because we're differentiating with respect to x. And so there's nothing to pop at the end. You don't put dx dx. Even if you did, dx dx would be 1, so it would disappear, right? When we do differentials, we pretend like dV dx is a fraction that can be broken up, and we go ahead and do a cross multiplication trick. And so this direction, I would say, that way's easy. dV times 1 is just dV. And this is equal to 3x squared dx. And here's how you're doing your approximation. We're using that for my dx. And then in terms of what I'm plugging in, what's x represent? If the volume is x cubed, what's x represent?
Flip side.
Mm-hmm. And how long did we say the sides were? 10. So you're going to do 3 times 10 squared. And then we said the dx we need to plug in is 0.2. And what this gives you is an approximation of the amount of paint that we used. So this is going to be 3 times 100 or 300 times 0.2. And 300 times 0.2 is 60. We're talking about a volume, so I'm going to say cubic inches for my units. The surface area of a cube is increasing at a rate of 4 square inches per hour. How fast is the volume changing?
dV/dt.
When the surface area equals 54 square inches.
dV/dt equals 4 inches squared.
So if we're talking about a cube and we know that a cube means all the sides have exactly the same square faces. If they don't give you a formula for the surface area, are you cool with how you would find the surface area of a cube? These are the types of ones where if they're not going to give you a formula, it'll be something like a cube because they're going to assume you can figure that out. Surface area on a cube, because it's a cube, each of the faces are squares, right? And so if we said that this side length was X, this side length is also X. So the area of one of the faces is X squared. On a cube, how many faces do we have? 6. So your surface area, I'll just say area, is 6 times X squared. Is that okay? Volume on a cube, we just did in the last problem. Volume is equal to X cubed. That one's not hard. Side times side times side. So they're telling us that the surface area of the cube is increasing at a rate of 4 inches per hour. So they're giving us that dA dt is equal to 4. And they want to know dv dt when the surface area equals 54. So when A equals 54. So if I go and I take my dv dt over here, I'm running into a problem because
Oh.
when I did that, I need to be able to plug in a side length of x, and I need to be able to plug in a dx dt, and I don't have either of those things, right? So it's not that this is a hard problem, it's just that if you go about it the way we've been doing the other ones, you don't have the things you need yet. So we're gonna have to use the other side to help us figure that part out. So when the area is equal to 54, if we come back over here, I can use this to figure out what the side length would have to be so I can get the x part. I don't have x, but I'm going to need x in that part of my formula. So what I'm going to do is use this part, and I'm going to plug in 54 right there. So 54 is equal to 6 times x squared. If we divide both sides by 6, that should be 9.
3 equals x.
Right, so our side length, we do have, x has to be 3. So I'll be able to plug in 3 right there. But I still need dx dt. How am I going to get that part?
Wait, we do the derivative of area?
So if I come back to this one again and I go ahead and I do dA dt, then this should be 12x dx dt, and that's where I'm going to be able to go get my dx dt. And the reason that's going to be okay is that they told us dA dt has to be 4, so I can put 4 in there. I know what I need to plug in for x now, and so I'll be able to go get the dx dt.
One over 3x.
So that'll be 36. So 4 over 36.
4 over 36.
Did you plug in the 3 right here for the x? Because you brought that down, you did 12x, right?
So that would be 1/9.
1/9. There you go. Now we have all the things we need. I have the dx dt is 1/9. I have my x is 3. So I'm going to come back over to, sorry, this formula right here. And so dv dt is 3 times, we're going to plug in the 3 for the x value. And then for dx dt, we're going to plug in 1/9. And so we've got 27 times 1/9 is 27 over 9, which would just be 3. And in terms of our volume, then that's inches cubed per hour.
dx dt equals.
dx dt was 1/9.
Oh, that's dv dt. Yeah.
Yeah.
Okay.
All right. I'm gonna end a little early there next week, I need you to check Canvas before you come to class. And the reason for that is that, my dad is dying, and it could happen in any number of days. They're not entirely certain if it's gonna be